Hi, everybody. I've been around for 7 years, as Christian introduced me. I've been doing lead application engineer for a lot of aerospace, also other industries in the region. So today, we'll talk about some technologies that has made their way recently into Nastran, and these actually are kind of toolboxes that are available for Nastran to simplify assembly level analysis. And those components that we'll discuss today are here in the agenda slide. So the first component we'll talk about, actually the first 2 points, do touch about contact. There's 2 kinds of contact primarily in Nastran. The first type of contact we'll talk about is glue contact, and how glue contact can help expediting the assembly mesh without having to define or modify your mesh to be congruent everywhere. So you can leverage the glue contact in linear solutions as well as in nonlinear solutions. As for integrating more realistic physics into your model, you might also consider to integrate linear touching contact into your simulation, also for linear and nonlinear solutions, and we'll talk about that in the second point. Then we'll make a brief coverage of the Nastran connector technology. These connectors also help simplifying and expediting assemblies into your FEM, and we'll talk about the different categories that are kind of good to use in conjunction with contact as well. And finally, we'll talk about how to define a bolt or preload into your simulation. Again, both for linear and nonlinear solutions. So these will be very quickly reviewed, and then we'll conclude with a little demonstration on how to define contact bodies, because it's at the heart of the presentation for today, and this will help you kind of getting an understanding of how to get on the rails with this fairly straight, very easy to define contact bodies and set up simulations for that as well. And we'll conclude with a question and answers session towards the end. So let's start by talking about glue contact, and I think the best way to talk about glue contact is showing a few illustrations just to kind of make you understand where you can actually leverage that capability that's now available in Nastran with linear solutions and nonlinear solutions. The values of glue contact, from my perspective, and I've worked with a lot of customers recently that have been trying to integrate this into their processes as we go, because there are several very high-level value that you can reap out of this methodology. And certainly the creation of large assemblies can benefit from glue contact. The fact that you actually have to sometimes bring different mesh components together, depending on where you stand into your in the chain of components that you design or build, you can yourself decide to mesh components which have different mesh densities for different needs, and glue them together for different reasons or different purposes very efficiently. And also the fact that you can also perform global local analysis into your models without having the need to define 2 different models. And this is especially useful when you have several load cases. So if you are of the traditional type of doing global local with different models, you know that you have to kind of map or transform the loads at the boundaries of that coarse defined mesh. And for each load case, you have to be extremely careful on how you transfer the load, make sure you have the equilibrium maintained, and also make sure that the orientations of the force and loads or displacement-based field is accurate. And that can be cumbersome to some extent. So first of all, glue contact, with the traditional methods of the last few decades in FEA using Nastran, people would actually spend a lot of time to actually assemble things together by having to move nodes or remesh and ensure that you have node congruency at the interfaces or mating interfaces of those different mesh components. Whereas you can now set up glue contact by defining components A, B, and C and stitch them or glue them together at their interfaces where they stand, and expedite at least have a good feel of the stiffness and load path very early in your design process. So this is where glue contact becomes very, very efficient, because you want to be able to get a system level response of your mesh under certain simulations, And you can do this without spending days or weeks trying to modify the mesh at the interface, or you have to locally remesh an area, and the transition makes it that you have to kind of really start to grow the mesh density on a large area. That sometimes is impractical, and you can actually, instead of having large transitions of triangular elements which will skew your stiffness, you can decide to just remesh locally to some extent an area and glue it to the coarse mesh adjoining it. Now, obviously, you have to use your engineering judgment when doing so, so you have to make sure that you satisfy the rules of FEA analysis, where if you have a large mesh ratio between a boundary from a large coarse mesh to a fine mesh, if that mesh density ratio gets too high, obviously the stress and strains might not be that nice in that area. However, if you move away from that boundary, it's like the boundary conditions basically, you can start to believe the results. But the good thing is that the load flow at the interface satisfy the equilibrium, and thus you can actually believe how the load path is behaving. So these are just illustrations. We'll go into a little bit more detail here. For an example, this wing rip was worked by one of our application engineer, and he was working with this to illustrate how to work with different discrete models. And I was able to actually take these two components, integrate into the same model, and glue it and get all the loads and distribution of stresses inside the rib, the detail rib, in about 10 to 15 minutes. So this is where actually it gets very, very interesting to be able to transfer the loads from a very coarse model to a detailed model in an efficient manner. Another very rewarding experience with glue contact was to kind of inherit the geometry from CAD geometry from this PC board assembly and directly mesh it as is, and keep the red chips or the red ceramics component standing out by half the thickness of the mid-surface of the shell, which is actually the green PC board there. And just defining glue contact, you could actually maintain that gap, and the solver will actually recognize the physical representation of the shell and glue the ceramics on the PC board. So traditionally, people working in this environment would maybe just perform non-structural mass of the ceramics on the PC board and perform, any type of statics or dynamics with it by kind of ignoring the effect of the stiffness on that PC board assembly. While sometimes, especially under thermal excursions or dynamics, the change of stiffness locally may affect how the stresses in the leads and the solder joints will be impacted. And in this case, the value of glue contact is the fact that once the glue is done, you can actually bring the solution to dynamics, eigenvalue analysis, modal response, transient, and so on. So we were actually able to do random analysis with this PC board assembly. Another value point for glue contact are when you're working with very thick structures. Could be like heavy machinery type of steel plates, or honeycomb structures like a 1 or 2 inches thick honeycomb, where you get the models from a mid-surface extraction or idealization from CAD, and then you spend a lot of time trying to clean up the geometry and extend and mesh and extend and match the edges at the boundary to get a nicely congruent mesh. So the benefit of glue contact in this case is certainly the fact that you do not have to modify the geometry. You just get the mid-surfaces where they stand. And because the solver will recognize the actual physical thickness of the shells, it will enable you to bond the edge or the corners, even though they are sticking out by half the thickness of the adjoining plates. So the first value there is that you don't have to modify the geometry, plus you get the exact mass distribution of the system. And secondly, you get more realistic corner stiffnesses, which is also rewarding depending on what the type of analysis you're performing. So this is just another illustration where glue contact can be valuable. And this one is certainly typical of larger OEM type of work where there's an integration of different components coming from different groups or departments, and you exchange models. And if you're working on the loads model at the higher level assembly, and you're hearing that there's been a design change in a subcomponent, but there's no coarse mesh available of that one. You can actually swap it inside the assembly level to some degree and integrate it directly and redo your analysis to evaluate the performance impact of that design change, either very early in the design process or very late, and usually very late you don't have much time. So modifying and recovering a coarse model idealization might take some work and effort, whereas here, just an illustration of how you can actually integrate it as part of the process and get very good, accurate results. And if you push glue contact into nonlinear using the advanced nonlinear solution 400, you can actually trigger breaking glue. And that concept is actually the solver will look on an incremental base if the normal stress and the shear stress at the boundaries where components or contact bodies are glued together against the criteria that you define. So you define an allowable for shear and normal stresses, and you can actually define some exponents depending on your correlations. If you have correlations that you have to relate to from tests, you can get very, very good results with this by pulling on it and looking at how things will disbond or break some sealing or fasten, or I was about to say seam joints. So that also works very well, can be used for bonded analysis, or if you want to understand how the load flows after a thing starts to fail, you can control it that way as well. However, just a note here that breaking glue is obviously a nonlinear only type of capability. So towards the end of this session, I'll do a little demonstration of how to set up that curved panel. So the curved panel actually is kind of illustrating different type of contact situations combined into a single example model. So we'll review the requirements and how easy it is to set it up and take a look quickly at the results. So I think I've talked through the glue contact benefits, is obviously to enable the user to quickly assemble things together without having to worry as much as for nodal congruency between the joining meshes. And obviously that may replace fasteners. You can actually leverage that for bonded assemblies when you bond different types of material together stacked. And bond happens on the shell edge as well as face-to-face contact type in that situation. Now let's move to the other side of contact, which is touching contact. So touching contacts obviously opens up the door to do much more higher fidelity mechanics into your simulations. A few examples here where typically in linear static solutions, if you don't consider contact, you have to revert back to hand calcs or handbook calculation types, or move to nonlinear altogether. In this case here, Nastran allows you now to perform linear touching contact to a certain degree. Obviously, you have to maintain some relatively small displacement, deformation, and small strain in your results for the results to be credible. But if you get started with linear static solutions and you have decent results that satisfy those criteria, then obviously you're up to getting much more realistic physics into your model where things will settle together and the load flow may be completely affected. The second example here in the middle of the page on the right-hand side is a type of ship hull structure where the large displacement is not too large with respect to the fact that the structure is pretty large, and not having contact triggered when there's pressure in that hull there on the outside, you will not capture the fact that it touches somewhere, which changes the load flow. Where here in linear static, when triggering contact between plates or 2D and 3D elements, you will have the right load distribution at the interfaces, and that's also true for type of fastened plate together where there's a heel and toe effect that's becoming quite apparent. I think we have an example here where the bracket is attached via the two fasteners on the top of that slide, and when you pry that bracket with some vertical or lateral load, obviously the edge will react to the plates, and that so that the load will not go through bending altogether in the fasteners, but will be distributed from a typical reaction load set of coupled moments and forces that is more realistic and more representative. Just to note here that we have an example that shows 3D to 3D contact, but we could swap either one of the two parts or both as shells and still perform the same type of analysis in 2D as well. Other situations where contact might be interesting if you want to simulate gasket pressure at the interface, make sure you have a good seal or Hertz in contact stresses. Obviously, this also enables you to get there without the need to define our traditional C gap in our nonlinear static solutions, solution 106 for those who know it. It's very tricky to get to convergence, especially when things start to slide and move in all sorts of directions. So this enables general type of touching contact with very complicated geometry without having to define any surfaces or anything. The only thing you need to define as a user to define contact is to select the component, which are what we call contact bodies, and define which contact body sees which other contact bodies in your assemblies. Usually it's a handful of those to define. It takes only a few minutes. Another valuable thing that I know that saves a lot of people in my past experience here is how to define interference fit. Again, simulation that can be done in linear statics where you just use the nominal dimensions of the assembly. You don't have to define the penetration by deforming the nodes at all. You can, if the nodes are actually at the nominal design location, without interference, you can force the interference by just punching in numbers between the contact body definition. Or if you have already interference fit in your mesh, you just let it as is, and at step 0 of the nonlinear increment process behind the scenes, even though it's a linear solution, Nastran will recognize that there's initial penetration and will move the nodes to the outlying surfaces and induce the pre-stress due to the interference fit naturally. So that becomes very easy to do as well. Another example where we have a lap shear joint with a pin, we can actually integrate, there's a steel sleeve inside an aluminum beam there, the blue and orange or gold shape color, so you can actually have the benefit of integrating this all together by meshing the components as is using 3D mesh very easily. And you notice here that for bearing stress in cylindrical holes, it's also good to have at least one of the sides to be meshed with hex bricks elements. That's usually very good practice to get very good bearing stresses as well. As part of this presentation, you'll be able to download some files, workshop type files for glued contact and touching contact. So this is the example how to set up a 2D to 3D contact bracket, very similar to the one I had on the previous page, and you'll be able to download the example files and reproduce on your end with Nastran. Quickly on the Nastran connector technology, not sure who is familiar with this, so it's good to have a good refresher on the fact that Nastran provides different type of fastener besides the typical bar beam or RB2, RB3 type of assemblies with multi-point constraints. So here's the description of what we can actually build assemblies and attach them together. The first two are the C-Fast and the C-Weld. These two connectors behave the same way in terms of definition. The trick here is that they only rely on a position in space. Once that position in space, if you look at the little quick reference guide diagram here, the GS location can be defined as a point, a geometry, or a node inside your model preprocessor like Patran. And once that point location is defined, regardless of how the mesh density is distributed for the two plates that you want to attach together, it will make a projection to GA and GB. And from that point, it will create the connector inside the solver architecture. So you will not have to worry about defining or creating the elements per se. Now, mind you, Patran offers the ability to do that, some expert as well. So you can create those fasteners and see where they lie in space. It's very useful. But the solver actually takes care of distributing the stiffnesses and connecting to the adjoining nodes using some MPC equations internally on both sides of the plates. Therefore, the user only has to carry the location in 3D space. So that's very rewarding, especially if you have to remesh either one or both of the sides and not have to worry to have line nodes that will match those fastener connection locations. So essentially, if you have like thousands of fasteners that are collected into a cloud of points, and you play with the mesh at a large scale, you can actually recreate the fasteners with one selection or based on the property definition of both plates. So you can create a fastener by saying, here's the position in space, and find the two closest plates that are projected on, and it will attach those plates together. So the C fastener works a bit like the C bush element. So it's a 6x6 stiffness matrix. And you can actually punch the numbers for carrying only translational or only bending or both, typical of C bush. And the C weld, instead of relying on the stiffness matrix, you define a material and an effective stress area. And the solver will actually derate the stiffness matrix from that kind of a short stubby beam approach and define it and calculate the stresses as well on it. There's also a third category of fastener, which is called a C-seam. The seam is actually a brick-like, it's not illustrated here, but it's a brick-like seam joint along plates, so that's also supported. In SimExpert, we have the ability to perform a creation of discrete elastic fasteners. So they actually are, it's some sort of a utility that actually manages the point location, enable you to create on the fly different type of connectors like bush, RB2s, but also chains of bush and MPCs, and also control the spot weld location. So you can actually define those, and if you want to, because you need that to happen in your model, automatically update the mesh so it matches those positions as well. Now, we talked about contact earlier, and now we're talking about fasteners. Can these work together? Yes, they can, and they will actually improve the way your physical model will behave. If you take a look at this little single-side lap shear joint, where I've on purpose only selected or defined a single row of fastener. I know it's not very design sensitive, but it's just to illustrate the fact that at the bottom right-hand side, you notice that if you have contact or don't have contact, without contact, all of the load and the bending will be carried by the fastener. Now, one knows that if you have sufficient length beyond the fastener row, some of the load or a good portion of the bending moment will be reacted by the heel-into effect of the tip of the plate. And actually, those plates should not have a relative rotation. And when you trigger contact with the fasteners, that actually happens, and you have a much more accurate result from your simulation. Now, the benefit of having more accurate and better fidelity on the mechanical realism in your simulation is that obviously not having as much load carried by the fastener will enable you to either reduce the number of fasteners or their size, thus affecting the mass and the behavior of the structure. So you can actually help reduce a lot of conservatism that's embedded in there. Or all of the work that's required to validate what do we do with the bending moments going through the fastener joints, and making less hand calcs or less assumptions where you can actually trip and make a mistake in your design process. Now the last component is use the fasteners in modeling tools, and both Patran and SimExpert have a little utility that enables you to create on the fly some fastener with preload. So this is key here is these utilities will create the bolt element. If you look at a quick reference guide under the bolt entry, this one I think has been introduced about 2 years ago in 2010. So the bolt enables you to pick a series of elements on one side and the other side, and the solver will actually manage the node relationship on the top and the bottom part, and will also manage the MPC constraints that will induce the preload at the interface. So obviously here, it's easier if you have a clean interface, as shown here with the fastener that's in hex mesh. It's doable also with tech mesh, but it's a little bit harder to select, but still it's doable. And it's also doable in using 1D beams. So if you have typical shell assembly models and you have 1D beam fastener, you can actually have just an extra node in the middle and break it there using that utility and induce the preload to the structure. So that makes it very easy to set up, and it will actually perform the work that you're looking at very well without having to do preload by inducing some thermal excursions. A lot of people that are trying to do this actually trip because at some point maybe you have a thermal case you have to consider, and then if you have your preload as a thermal case, you have to still compound the effective temperature on the subsequent load types. So this is not the case here. So preload is also available in linear static solutions, and you can also do preload and pre-stiffening and keep that state to do eigenvalue or modal analysis downstream in the process as well. So that pretty much concludes what I wanted to kind of cover with you in terms of technology, just to increase awareness that all of this technology is in Nastran today. You can use it. That most of it has been introduced in 2010 and on. It's been improved as well. Contact makes significant improvements every release nowadays, so we invite you to give it a try. And if you want to get on the rails quickly, you certainly can contact your local application engineer like myself in your area and start to look into example models. Nastran, in the Nastran documentation, there's a user's guide or a guidebook for Nastran contact simulation type and also nonlinear simulation types. It's called the user's guide, the Nastran contact user's guide or something like that. Sorry, I missed that one, but I can show you later. But there's tons, at least close to 100 problems, example problems there where you can follow and get started pretty quickly. So before we go to the Q&A, I'll just bring my little example model here where we can define contact bodies and perform glue contact for that little curve panel here. So this model is prepared. The only thing that's defined in here are the material definition, the properties, and the boundary condition. So if I just illustrate what are the boundary conditions that we'll consider for that, we'll consider a pin on the outside, actually the top and bottom only, so we're pin at the top and bottom, and we just apply an internal pressure, okay, on the structure. So that's for the load case. Now, once we have the load case and we have the structure organized into different groups, and you'll notice here that I've made groups of components that are kind of similar, and we'll use these groups to quickly define the contact bodies. Now, while I define the contact bodies and set up the job for contact, I will kind of try to emphasize on the little gotchas that people trip on, or little tricks that can make it easier for you to define that process. So the first thing we do is we notice that contact definition for the formal bodies is under loads and boundary conditions in Patran. So we go to that menu and we say create contact deformable body. And in this case, we have a few to define. And we'll define them by the fact that they kind of shared a similar contact nature and also similar mesh density. That will help how we actually come up with a very good solution quickly. So the first one we'll create is the one that's called the coarse shells, which is the coarse shells that are orange here. So we will define this as a single contact body. And you'll notice I'll be doing this a few times now from this point down to the end of the demonstration. You don't have to create a contact body for each zone. The contact is general, so it's generic. It will find the locations of the adjoining other contact bodies that you define on the contact table, so that these pairs of contact bodies will actually will not really matter if they actually are disjointed like this. So that makes your life much easier in terms of defining those contact bodies. So we'll do coarse shell. That's the name. It's going to be 2D elements in this case. We'll pick the region. And notice that when you press apply, you'll see those magenta dots in the middle. This is how we illustrate, similarly to loads and boundary conditions, the contact definition of a certain element. Now we can move to define the ribs. So again, a typical, not necessarily mistake, but typical behavior from new users that are using contact is that they will actually create two contact bodies for those two ribs. If the contact definition to their adjoining bodies is similar, you can actually just create a single body for those two. That saves you time, and it works very well. So we'll say 2D ribs. Again, these are 2D elements. Now we have the find panel, which is maybe a local kind of reinforcement that we want to attach some components or other components later on. So we have these two, and we also have the window. Now, again, they have similar mesh density, even though the window is smaller, but the contact with the remainder of the structure is similar, so we can actually join them together and say these will be 2D fine. And once that's done, we're nearly to the end. Let me post this. One good practice is obviously to ensure that we have not left anything out of the contact definition. So we can actually plot the markers, and plot contours is better. So plot contours, contact, just to verify that we've defined everything. And notice here that contact contour will be based on the color scheme of the outside of the element, so the edges of the element. So we have the dark blue for the coarse shells, the yellow for the 2D ribs, and the fine for the green detail mesh. So we're good here. Now let's go to the analysis setup. So we're going to set this analysis by specifying most of the things will remain default. So we're going to use Nastran 2012. Solution type is linear statics, solution 101. The only thing we may actually want to do here is control the fact that we'll ask for master DBL. So I want to make sure that instead of using XDB, we'll use master and DBL. And the reason for this is that when you do contact definition in Nastran, it's always good to request for contact output. Contact output will ensure that every node that you expect will be in contact with another body will be actually in contact. And that's pretty, it's as important as verifying your equivalency when you verify your model. So that's quite important. You'll notice here that in solution 101 here you have linear static solution. We have contact parameters. So we will consider all the defaults at this point here. There's certain higher level control parameters that you can play with here. This is where you would define a friction, for instance, as a global friction parameters for your contact simulation. We'll go to the subcase. So we'll create subcase called default in this case. Subcase parameters. This is where we'll actually get to our contact table. And the contact table is, this is interesting. Deactivate everything here. So contact table is where you define contact, how to contact will occur in your simulation on a pair-by-pair basis. So in this case, if you look here, touching body and touch body, this is a methodology where you say, okay, my 2D fine ribs will touch the coarse shell, as an example. And you see here, there's a highlight on that box here, which is 1, 2, 3, which is 2D fine, 2D ribs, and coarse shell, with 1, 2, 3, how this one touches this. If you click in the box here once, a T appears. So this means it's touching contact. Touching contact is that you imply that it will touch at some point and may separate. It's not the case here. We want to do glue. So if you click again, then you define a glue contact between two bodies. We'll set it to automatic contact detection. There's a few options here, though. This is 2D fine to coarse shell. So this is what we call edge-to-edge contact. Now, if you pay attention here on this edge, this horizontal edge, that's good because they're all in line. There's no problem that will occur here. However, if you notice, I'm trying to move behind the scenes here. you notice here, we have a curved structure where the finer mesh density follows a more precise arc, and there's a gap there. So that edge-to-edge gap will have to be closed, and the solver needs to understand that you want to stitch those two edges, the coarse edge to the fine multi-node edge together. So the way to do this is to control the distance tolerance error, which is the error outside the normal. Actually, it's in the normal direction, but outside the plus Z or minus Z of the top and bottom skins of those shell elements. So you can actually increase that to ensure that you close that gap on both sides. So whichever node looks for the adjoining contact body that it will touch, if that zone is opened up a little bit, it will close that gap automatically. And the way to verify this is to use the contact status. That's only available in the master DBL. So that's why I've asked for master DBL as output. So in this case, we have a 2D course to the 2D fine, and I've made verifications on this one. We have to have a definition of 0.03 to make sure that we close this nicely. Okay. So usually contact definition, if you have it the first time, that's good, but it may happen that you have to iterate one or twice just to make sure that you cover all the little gaps and different subtleties in your model. So that's really model dependent. We'll retain those gaps. So we'll say to the solver, don't try to match the mesh and move nodes around. Keep the mesh as is, retain that gap, and make the right calculation for moments that will be carried at the interface. So we have to check those two boxes, just best practices or typical practices for that type of edge-to-edge contact. And edge-to-edge contact, we have to specify contact boundary. We define ignore thickness on both sides. Ignore thickness means that because of plate theory, we only carry the bending moment through the neutral axis. If you say do not ignore thickness, it will notice that there will be contact at the neutral axis, but it will actually define contact at both minus Z1 and plus Z1. And that will actually induce some kind of dummy moments on the skin surfaces on both sides. And actually, this is not right. If you want to maintain stiffness, that's because you want to carry bending moment across like a plate edge to a surface of a solid. But in this case, what we want to maintain is the continuity at the neutral axis to carry the right bending across the boundary. So this is how you define that. These are just guidelines that we typically give into our training material for contact. So we have one contact pair defined. The other two are similar. The other two will be the 1D rib to the coarse face-to-face, and the 1D rib, the 2D rib, sorry, to the fine mesh. So these two contact definitions will be the same. So similarly here, you'll notice that the gap distance, I'm trying to find a way here to show this exactly. Okay, so you'll notice here, depending on where we, oops, try to put it here. I'm just trying to zoom in. You see here that gap from element to element will be different because we have a different radius of curvature. Therefore, we also have to open up a little bit the tolerance on that side. So what we'll define is we'll define the 2D ribs to the fine mesh, this guy here. So we go to this box, define glue, and we put a 0.02. That's sufficient. We have to define retain gaps and retain moments. However, we have to keep the thickness. We need to have the solver to understand that these faces extend there, and the contact will occur at the plus and minus T/2 thickness. So in this case, we leave it on. And we do the same thing with 2D ribs and coarse mesh. This guy here with the same kind of gap opening to cover the gap because of the arc difference. And retain gaps and retain moments. Once this is done, I think we're good to go. Let's make sure that we have B output. So there's an option to select here what we call B output, which is the contact results. This is what is going to trigger the output for generating contact results, just to verify that everything touches initially on our run. So yes. There's a little bit of lag here. I think it's because of the WebEx, or yeah, I think the shared pop-ups on my screen actually take a long time to display. So bear with me here. We have only this subcase defaults, which is the pressure case. I'll submit that to Nastran right now. All right, I think once we're over the hump, we'll be okay. That's good. So now Nastran is running. You may notice that my Exo 6 report, for those who are not familiar, I've built a utility that actually collates all Nastran output and puts it and pops it up, so you know exactly when Nastran run, and you know if you can improve performance of your jump time. And also it will highlight in color code if you have a successful run. And you can actually highlight the SPC force resultant, so we know that we have 100 pounds total here. So we have results. We don't have a failure, so we can actually go and with some confidence attach the results. I will attach the master. As I mentioned, I'm using the master because I want to be able to review the contact results. Here. Okay. So if I zoom it, yeah.
Dominic?
Yes.
We hear, or the audio seems to be dipping in and out. I don't know if you're close to the phone or not.
Okay, I've moved the, yeah, I have a notepad here where I punch to punch the right numbers. So I've moved the phone closer here. Is it better?
Okay.
Sorry about that. All right, so notice here that we have subcase 0 and subcase 1. Now, bear in mind we're running solution 101, linear statics. Contact obviously is a nonlinear process behind the scenes. And in this case, the only component of nonlinearity is the fact that initially we define contact. So the solver goes at step 0 from an incremental base and will check if contact happens. And it will generate the contact status at step 0. So if we do press on that one here, we have the contact status output. And we can actually display the contact status. Let me put the element edges on. It's a little bit more rewarding. And we see that we have regularity in the contact definition. So everything seems to be touching perfectly at the interface, which is a good sign. So you always have to verify this. Now, the fact that we have not a white band and we have those red strips here, that's because we have a cascading contact here. Because the refined mesh touches the coarse mesh, but also touches the rib. So the cascading effect will actually let the solver decide if one is touching or the other one is touched. But this requires like minimal practice to understand if it's good or not. But essentially here, what it tells me is that everything's touching in a very regular fashion. That's kind of very important to verify. If not, you can get fooled by the results and miss the fact that some nodes are not really touching, and then you have like a non-equivalence model, which is not good. So we'll go back to the results and display the displacements. Just illustrate here. Obviously, I have to look at subcase 1. So that's my traditional static subcase here. All right, and if I put the deformation to amplify the results, just to make sure that everything's stitched together, amplifying it will help determining that there's no gap opening. So we see that there's continuity in the mesh, and this is like a large-scale amplified separation or displacement field. So that's very good. Obviously, you can go about and display the stresses. Von Mises and an indication. You will see now that the von Mises stress, obviously those boundaries from coarse to fine are very narrow. So in order to look at the stress field in a very irregular manner, you'd have to kind of maybe remesh a little bit differently to get away from the edge effect. But still, we have a fairly continuous field altogether. Yeah, it's like any boundary condition. If you put like a singularity in some point in your model, you have to, look at stresses and strain a little bit far away from it. Otherwise, you'll get kind of affected by the proximity of that singularity. And the last component or topic I want to talk about here is that we've talked about the integrating local and global models. So the interest also for people is to understand how was the load map at the interface. So can we display that? Yes, a grid point force support is supported at for glue interface. So if I simply post my window and I zoom in, and we do the free body plot, and I will turn off the Z, which is a pressure, because we have a pressure, and there's going to be arrows. If not, there's going to be arrows everywhere on that model. So let's put the boundary forces, and we have the load flow at the boundaries. So this is just to illustrate that you can recover and report back all grid point forces at the interfaces of every section that you make of the model. So that's also very, very useful for people that do global local analysis with glue contact. All right, so that pretty much concludes what I wanted to discuss here regarding different methodologies using Nastran to assemble efficiently your structures and models. And I hope that at least you're able to pick up a few new ideas about how to improve your processes. And I invite you to ask us questions and also contact your local application engineer to get these processes reviewed by your team and use them.